Hi, everyone. Welcome to week 9, and today we're going to talk about factorial ANOVA, and we're going to look at main effects and interaction effects in a two-way ANOVA. So conceptually, we're going to talk today about the meaning of two-way factorial designs. We're going to talk about what marginal means are and main effects versus interaction effects when you have an ANOVA with more than one factor. We're going to see what an ANOVA output table looks like for a two-way factorial design, and we're going to talk about how to interpret main effects versus interaction effects. Next week, we'll talk about assumptions underlying two-way ANOVA. We'll talk about more complex factorial designs, and importantly, we'll talk about post hoc or follow-up tests and how to interpret them, and importantly, how to correct for type 1 error for multiple comparisons. Okay, so when would you use a factorial ANOVA? Basically, when you have two or more independent variables or factors, and you want to test the main effect of each factor, and you're also interested in testing the interaction effect between factors. And we'll talk about what that means. Just a word about notation. A 2 by 2 factorial design, so 2x2, that means there are two independent variables, each with two levels of the first factor and two levels of the second. So it might be placebo versus drug in males versus females. A 2 by 3 factorial design means there are two independent variables, one with two levels, that's the first two, and the second factor has three levels. So that might be males versus females for factor 1, and placebo versus drug 1 versus drug 2 in factor 2. A 3 by 4 factorial design still has two independent variables, two factors. The first one has three levels, and the second one has four levels, and so on. So when you see that number x number notation, that's what it means. So just in chart form, a 2 by 2 design means that every level of the first factor is tested within every level of the second. So on the top, we have independent variable 1, which has level 1 and level 2. And on the left, we have independent variable 2, which also has two levels, 1 and 2. So in a 2 by 2 design, there are four possible categories. There are four possible cells, as they're called, in this 2 by 2 design. So here's a specific example of a 2 by 2 design. We might vary the time of day, morning versus afternoon, and then within each of those levels, we might test some caffeine versus no caffeine. So we have all four combinations. Morning some caffeine, morning no caffeine, afternoon some caffeine, and afternoon no caffeine. In a 2 by 3 design, one factor, one variable has two levels, 1 and 2, and the other variable has three, 1, 2, and 3. So we might still have morning versus afternoon as two levels of one factor, time of day, but now we have three levels of the second factor, caffeine. One coffee, two coffees, or three coffees. And clearly 3 coffees wins. So importantly, each level of coffee, 1 versus 2 versus 3, is tested within each level of time of day. So in a 2 by 3 design, you have 2 times 3 equals 6. 1, 2, 3, 4, 5, 6 different possible cells or conditions. I should mention, in the factorial ANOVAs we'll talk about today, participants in each cell of this design are different. So it's a between subjects design. Each participant only contributes a score to one of these 6 cells. A repeated measures design would be when the same participant provides a score in different cells, but we're not going to talk about that today. It's a bit different. So we've talked about factorial designs, and I want to talk about what the word factorial means. So an experimental design is fully factorial when the levels of each factor are fully crossed with the levels of each other factor. That means each level of one factor is tested in every level of the other factor. So in a 2x2 design with factors A and B, there are 4 conditions: A1, B1, A1, B2, A2, B1, and A2, B2. So this design is fully factorial because there are data for each of these 4 cells or conditions of this design. In a 2x3 design, A1, A2, and B1, B2, B3, there would be 6 conditions: A1, B1, A1, B2, A1, B3, and then A2, B1, A2, B2, and A2, B3. This design is also fully factorial. If one of those conditions are missing, then it's not a fully factorial design, and the analysis of that kind of data set would be a little trickier, and we're not going to talk about that today. That would be an unbalanced design, and they're pretty awful, to tell you the truth, to deal with. So we'll talk only about fully factorial designs today. Here's some example data that you can load into R on your own. It's a data file on the course website called clinicaltrial.rdata. It's from the Navarro text. So the dependent variable is mood gain, some measure of how much your mood improved. And there are 2 factors here. Factor 1 is drug, and factor 2 is the kind of therapy these hypothetical patients receive. These are made-up data. These are not real data. We've got 18 observations, so 18 different participants, and each participant only contributes a score in one category. So for each of the 3 drugs, placebo, Angzi-free, and joyzepam, we have people that were tested either with no therapy or with cognitive behavioral therapy, CBT. So it's a 3x2 design, so there are 6 possible conditions: placebo no therapy, placebo CBT, Angzi-free no therapy, Angzi-free CBT, joyzepam no therapy, and joyzepam CBT. And on the right is a plot of what these data look like. So let's talk about marginal means and what they are, because you'll encounter that phrase a lot when you read about 2-factor ANOVAs. Marginal means, it's very simple in fact, they're just the average of the dependent variable for each level of a factor when you average across all levels of the other factor. Or another way of saying it, you just ignore the other factor. So the marginal means for drug would be the mean score for each level of drug across all levels of therapy, regardless of whether it's no therapy or CBT. So we'd essentially just lump all of the therapy conditions together. So the marginal means for drug would be 3 of them. There would be 1 for placebo, 1 for Angzi-free, and 1 for joyzepam. And so for placebo, we would just take all the scores for placebo: 0.5, 0.3, 0.1, 0.6, 0.9, and 0.3, regardless of whether the scores are for no therapy or CBT. And for Angzi-free, we would do the same: 0.6, 0.4, 0.2, and 1.1, 0.8, and 1.2, ignoring the fact that there are different levels of therapy. And the same for joyzepam. Similarly, the marginal means for therapy would be the average across all levels of drug for the no therapy group and for the CBT group. So we take all the scores corresponding to no therapy, that would be the first 9 scores here, and we'd ignore the fact that they are placebo or Angzi-free or joyzepam. We just lump them all together, and then for CBT, it would be the last 9 across all levels of therapy. So marginal means just means averaging over levels of a factor, ignoring the levels of the other factor, or lumping together the scores across all levels of the other factor. In R code, we can use the summarize and group by functions to do this. We've seen this before already. So we could group by drug and then summarize the mean mood gain across drug levels. That would give us the marginal means of drug. One mean for placebo, one for anxiety-free, one for joyzepam. To get the marginal means for therapy, we could do the same thing, group by therapy and summarize the mean of mood dot gain across the two levels of therapy. And we would get our two marginal means of therapy. Pretty easy. There's also a function that you might see called aggregate, which gives you the same thing, but works in a different way. Instead of this tidyverse kind of way of doing things, where you group by and summarize, in aggregate, you pass it a formula. Just like a formula for a linear model. Mood gain varies with just drug. So ignore the fact that there's anything else. And the function I want is the mean, and I get the marginal means across the levels of drug. For therapy, I say mood gain varies with just therapy. Ignore drug. The function is mean, and I get the two means, the two marginal means of the therapy factor. So now that we have marginal means, we can ask the question, is there an effect of drug on mood gain? So if we look at the three marginal means of drug, that sure looks that way. Placebo is the lowest, anxiety-free is higher, and joyzepam is even higher. Is there an effect of therapy on mood gain? Well, perhaps. If we look at the marginal means of therapy, we see no therapy is 0.7, CBT is 1.04. That seems higher. Is it significant? Well, that's what we need a statistical test for, and so we can use Anova to test those effects. So let's use Anova to test those two marginal means effects, and then we'll move on from there. So one way we could start is we could fit a one-way Anova, like we've seen already, to test the main effect of the drug factor, and just ignore the fact that there's different levels of therapy. So marginal means correspond to a main effect. That's what it's called. So we can make a linear model. Mood gain varies with what? Just drug. Ignore therapy. And let's look at our ANOVA. And we get a very significant F statistic. F is really high, 18.6, and the p-value is really small, 0.0000865. Okay, well, it sure looks like there's an effect of drug on therapy. And if we look at the plot, we can see a similar thing. Placebo, now this doesn't plot the marginal means, this plots all 6 conditions. But you can imagine the marginal means for placebo as just the average of all these data points. They would be sitting somewhere in the middle. And so you can see placebo and then anxiety-free is bigger, although only for the green, not so much for the orange, which we'll talk about later. And then joyzepam is the highest. So it sure seems like there's an effect of drug. What about the main effect of therapy, ignoring drug? Well, we could make a new linear model. Mood gain varies with just therapy and include all the data across all drugs. And, now we get a much smaller F, and we don't get a significant result. So the p-value is not lower than 0.05. So according to this model, therapy does not have an effect on mood gain. Now, look at the data plot below. I would believe that for joyzepam. If you're taking joyzepam, it doesn't much matter whether you have therapy or not. Your mood gain is the same. If you're on placebo and you get therapy, maybe it looks a bit higher. This mean is higher than that mean. Is it higher enough to be significant? I'm not sure. What about anxiety-free? It sure looks like from the plot that if you're taking anxiety-free, therapy has a big improvement in mood gain versus no therapy. But when you combine this with the other two drugs, it kind of gets lost in the wash. So we'll talk about that in a second. But that's the main effect of therapy, and it's not significant according to this model. So we made a linear model to look at the main effect of drug. We made a different linear model to look at the main effect of therapy. We can do better than this. And the way we can do better than this is if we make one model that includes both factors together, kind of like a multiple regression, where we had a dependent variable that varies with multiple independent variables. Same idea here. So each main effect in this Anova design accounts for a different portion of the total variance in the dependent variable. And we can guarantee that because unlike multiple regression, where the independent variables can be correlated with each other, here, because it's a factorial design, the different factors are by definition independent from each other. So each main effect takes a unique bite out of the total variance in the data. So let me illustrate this with this new model here. Mod.both equals linear model. Mood gain varies with drug plus therapy. Just like in a multiple regression. Drug plus therapy. And let's look at our Anova table output. So we have the main effect of drug first, and just have a look at that line, that row, and compare it to the one on the left where drug was the only thing in the model. The degrees of freedom are the same, the sum of squares is the same, the mean square is the same. The F value is different, which we'll talk about in a second. The next row shows the main effect of therapy. And again, let's compare it to the model on the left where therapy was the only thing in there. The degrees of freedom is the same, the sum of squares is the same, and the mean squares is the same. The F value is different. And then finally, let's look at the last row, which is residuals, sometimes called the error term. It's the leftover variance that's unexplained. The degrees of freedom in the combined model is 14, which is smaller than it was in the individual models, 15 versus 16. And that's because just like in multiple regression, each time we add a factor to the model, each time we add an independent variable to the model, we have to pay for it using some of the degrees of freedom from the residuals. Therapy has 1 degree of freedom because it has 2 levels. 2 minus 1 is 1. Drug has 2 degrees of freedom because it has 3 levels. 3 minus 1 is 2. So those 3 degrees of freedom here come out of the residuals. The other thing you notice is the sum of squares residuals in this combined model is smaller than the sum of squares residuals in each of these individual models. And that's simply because each time we add a variable to the model, its sum of squares is calculated and it gets removed from the leftover. So each time we account for more sum of square variance, we take it out of the error term. We make the error term smaller. So the mean square is just the sum of square divided by degrees of freedom. And the F value, of course, is the mean square divided by the mean square residual. And so that's why these F values here in the combined model are bigger than the F values here in the individual models. The mean squareds are the same, 1.7267, 1.7267, 0.4672, 0.4672. They're the same. What's different is the mean squared residuals. It's 0.0928 in that model, 0.2736 in that model. In the combined model, it's smaller. It's 0.0660. And that's because the sum of squares is smaller. It's smaller because we've taken a bite out of the total variance by accounting for these 2 factors. And so when you take these mean squares that are the same as over here, and you divide by a smaller mean squared residual, you get a bigger F value. Now, it doesn't make much difference for the drug factor because it was already significant in the individual model. But look at the therapy main effect. It is now clearly statistically reliable. The F value is 7 and the p-value is 0.0187 In the individual model, the F value was only 1.7 and the p-value was way above 0.05. So how come the drug main effect gets flagged as significant in the combined model and not significant when it's tested on its own? Well, the simple reason is the error term is smaller. In the individual model, the error term is big. The variance that we haven't accounted for is quite big. In this combined model, we've accounted for two chunks of variance in the data, the variance due to drug and the variance due to therapy. And so the leftover variability is much smaller. And so when we divide the mean square factor by the mean squared error, we get a bigger F value and it's significant. So another way of saying this is each time we account for more variability in the data, the power, the statistical power of the effects that are in the model gets bigger. The variance that's accounted for by those individual effects doesn't change, right? The sum of squares and the mean squares is the same here as it was here. What changes is the denominator, the error term. And by making it smaller, we're making our tests of the factors more sensitive. We're more able to detect statistically reliable differences when they exist. Now, how come we just don't, we've accounted for two things in our data. How come we don't just throw 15 other things in there that we've measured post hoc? We would account for more variability, but we'd have to pay for them with a degree of freedom from the error term. And the mean squared error is the sum of squared error, the unaccounted for sum of squares divided by the degrees of freedom. So if the sum of squares residuals doesn't decrease very much further if we add more and more stuff, but this gets smaller and smaller as we add more stuff. So this doesn't change much, but this gets much, much, much smaller. Then this divided by this is going to be bigger than that. And that's the denominator of our F statistic. And so if that's bigger, it's bad for us. So by normalizing sum of squares to degrees of freedom to get mean squared, we're essentially building into this calculation a trade-off between how much variability is left over, but how many degrees of freedom did we have to pay to get there. So it penalizes throwing in a whole bunch of useless stuff that only decreases this unaccounted for variance a little bit. Okay, so the point of showing you all this was that by putting the two main effects together in a model, we get more statistically powerful tests of those main effects. And we do that because our error term gets smaller. Let's look at this mathematically. I don't mean to harp on this too much, but it's important to see how this works arithmetically in the Anova output table. So the sum of squares total, the total sum of squares in the model is equal to the sum of squares drug plus the sum of squares residuals. 3.453 plus 1.392 is 4.85. In this model where there's only drug, the total sum of squares is 4.85. In this other model where there's only therapy, the total sum of squares is the sum of squares therapy plus the sum of squares residuals, which is also 4.85. It's the same. The sum of squares in the data doesn't change. That's the total. In the model with both main effects in it, we still get the same total sum of squares, 4.85. That's because we have the sum of squares due to drug, the sum of squares due to due to therapy, and then the leftover, 0.924. So you can see if we had a third factor to put in there, that would get subtracted from here. This would get split. The sum of squares residuals would get split into sum of squares due to a new factor and then the leftover. The total would be the same, but the error term would become smaller. We'd take a bite out of the error term. So the more factors we add to the model, the smaller the sum of squares residuals. That's almost guaranteed. Now, how much smaller does it get? That's an open question. And remember, each time we add a new factor to the model, we have to reduce the degrees of freedom residuals down here. And that's what gets divided from sum of squares to get mean squared. So there has to be a big enough reduction in the sum of squares to justify the reduction in the degrees of freedom to make this thing smaller. Okay, so we've shown that testing each main effect using separate individual linear models is not so good. If we combine the two main effects in one model, we get more statistical power. But we can do even better than that. Since we have a factorial design, since each level of one factor is tested within every level of the other factor, we can add a third effect to the model, which is called an interaction term. So we can add a term that reflects the interaction, if it's there, between drug and therapy. And we do this in the linear model using the following notation. We would say mood gain varies with drug plus therapy plus drug colon therapy. The colon means interaction term. There is a shorthand by saying mood gain varies with drug times therapy. The times is shorthand in R to indicate you want to include both main effects and the interaction. If this was just a plus, it would just be the two main effects. When you make this a multiply, it tells R, I want both main effects and the interaction effect. So if we enter that model into R, mood gain varies with drug times therapy. Now we get an Anova output that has, just like before, the main effect of drug. Those numbers are the same as the individual model. The main effect of therapy, those numbers are the same as the individual model. And now we subtract from our sum of squares residual a new chunk of sum of squares. The sum of squares due to drug colon therapy, the interaction between drug and therapy. We have to pay for that using 2 degrees of freedom that come out of our residuals. But now, when we look at our mean squared term, it's even smaller than it was over here in the version of the model with just the 2 main effects. So we've reduced our error term even more. So now our main effect of drug is even more significant than it was before. Our main effect of therapy is even more significant than it was before. And now we have a third effect. We have a third effect in our model, which is the drug by therapy interaction effect. And in this example, it's not statistically reliable. 0.1246 is the p-value. Okay, so by including a third element, a third effect in our factorial design, the drug by therapy interaction effect, we've achieved a couple of different things. First, we've reduced our error term even more, which makes these other tests even more statistically powerful, more sensitive to spot differences. And we've enabled ourselves to test another effect in our data, the interaction effect of drug by therapy. We know what the main effects are. Those reflect the marginal means. But now we have a different test, which is the interaction effect. And we'll talk about what that means shortly. So we have a model now with 2 main effects and 1 interaction effect. The sum of squares residuals gets even smaller. It reduces the unexplained variance in the dependent variable. The denominator of the F statistic gets smaller for each of the tests of the effects. Our F values get bigger and our P values get smaller. So we get more statistically sensitive or powerful tests. Okay, so that's the sort of consequence of including this interaction term. But what is an interaction effect? Here's a good definition. An interaction occurs between 2 factors when the effect of one factor on the dependent variable depends on the level of the other factor. Or to say it differently, the difference in means between the levels of one factor is different for each level of the other factor. So an interaction is a difference of differences. Let me say it again. The difference in means between the levels of one factor, like therapy versus no therapy, the difference between therapy and no therapy is different depending on what drug you're on. For some drugs, the difference might be small. For other drugs, the difference in therapy versus no therapy might be big, kind of like we saw in this scatter plot here. The difference in therapy, no therapy versus CBT, is very small if you're on joyzepam, but it's very big if you're on Angsi-free. So that's a difference between these two and a difference between those two. This difference is smaller than that difference. So it's a difference of differences. Here's another silly example from Twitter, when Twitter was still called Twitter. This is a plot, I think it's made up data, although I believe it. It's a plot of the deliciousness rating of a sandwich when there's either no avocado in the sandwich or there is avocado. That's one factor. And the other factor is whether there's bacon in pink or no bacon in green. So regardless of whether there's bacon or not, adding avocado to your sandwich, it increases the deliciousness, right? If there's no bacon, then avocado is more delicious than no avocado. If there is bacon, avocado is more delicious than no avocado. But the effect of avocado on the deliciousness depends on whether bacon is present or absent. So this difference between avocado and no avocado in green, that vertical difference, is smaller than this vertical difference in pink between avocado and no avocado. So I'm just eyeballing the numbers here. But if bacon is absent in green, then avocado increases deliciousness by 3. You go from 1 up to 4. So 1 to 4 is an increase in 3. When bacon is present, avocado increases deliciousness by 6, by double. You go from 3 up to 9, right? 3 up to 9. That's a difference of 6. So 4 minus 1 is different than 9 minus 3. 3 is different than 6. So it's a difference of differences that defines an interaction effect. So the effect of avocado on deliciousness is different depending on the level of bacon. You get a bigger effect of avocado when bacon is present compared to when bacon is absent. A difference of differences. So that's the definition. That's the textbook definition of an interaction term, or an interaction between two factors. Let's look at some more cartoon examples. So here's an example of a 2x2 design. We've got one factor called A with 2 levels, level 1 and level 2, and another factor called B with 2 levels, level 1 and level 2. We can ask the question, is there a main effect of A? A main effect of A would be the mean of A1, averaging over B1 and B2, which would be this black dot, compared to the mean of A2, averaged across all levels of B, 1 and 2. That will be this black square. So is that black square different than that black square? And I'm just eyeballing numbers here. This might be 10 plus 20 divided by 2 is 15. This is also 10 plus 20 divided by 2 is 15. Is 15 different than 15? No. 15 minus 15 is 0, so no main effect of A. Is there a main effect of B? Yes, probably there is, right? A main effect of B would be B1 in orange averaged across A1 and A2. So 10 and 10, the average is 10, versus B2 in cyan, which averaging across levels of A. So 20 and 20, the average is still 20. So 20 minus 10, that's a big difference, right? So probably there is a main effect of B. Is there an interaction between A and B? No, I don't think so. Because the difference of differences is not different. The difference between B1 and B2 in A1, so 10 versus 20 in A1 is not different than B1 and B2 in A2. So this 10 versus 20 is not different than this 10 versus 20. That vertical distance is the same as that vertical distance, so there would be no interaction effect. The effect of A, so going from A1 to A2, does not depend on the level of B. A1 to A2, it stays at 10. B1 to B2, A1 to A2 within B2, it also stays the same. So those differences are also not different. So there are no difference of differences, so there's no interaction effect. And a general rule is, in a factorial design, if the lines are parallel, then you have no interaction effect. Because whatever's happening on one line, the same effect is happening in the other line. So that's by definition not an interaction effect. When the lines aren't parallel, you might have an interaction effect. Here's another example. Is there a main effect of A? Probably yes, right? The main effect of A is when you average across levels of B. So A1 averaged across B would probably be 10, and A2 averaged across B would probably be 20. Is 10 different than 20? No, let's say yes. So there's a main effect of A. What about a main effect of B? Probably also yes. A main effect of B would be if you averaged across levels of A within B1, which would give you this black square, and you compared that to the average of the two levels of A within B2, that black square. And again, 10 versus 20, probably there is a difference, so there is a main effect of B. Now, we're not doing statistics on these, we're just eyeballing it. Is there an interaction effect, A by B? Probably no. The lines are parallel, and so the difference of differences is the same. The difference between B1 and B2 within A1, here on the left, is probably the same as the difference between B1 and B2 within A2. So the effect of B is the same in both levels of A. Or you could say it the other way around. The effect of A, A1 versus A2, is the same across the two levels of B. What about this situation? You should already have a hint. The lines aren't parallel, so we probably have an interaction effect. Is there a main effect of A? Yeah, probably there is. A main effect of A would be if we average across levels of B within A1, that's this black square, and compared it to the average of A2 within levels of B1 and B2, averaging across these two, which would probably be that black square. So yeah, probably this one is different from that. So yes, we would have a main effect of A. Is there a main effect of B? Well, let's say yes. A main effect of B would be if you take B1, which is the orange line, and you average A1 and A2, and you get this square, and you compare it to the average of A1 and A2 within B2, which would be this black square. Are those different? Let's say yes. Is there an interaction effect? Probably there is. And that's because the difference between B1 and B2 in A1 is different than the difference between B1 and B2 in A2. So this difference, B1 versus B2 within A1, that difference is different than that difference. So we have a difference of differences. Same thing here. Probably there is a main effect of A. Probably there is a main effect of B. And yeah, there probably is an interaction effect because dog barking. The difference between A1 and A2 is different within B1 versus B2. Or you could say it the other way around. The difference between B1 and B2, that's these vertical distances, this difference between B1 and B2 is different than that difference between B1 and B2 within A2. So we have a difference of differences, so yes, we have an interaction effect. Here's another example. Do we have a main effect of A? Probably no, because if we average these 2 points, so if we average across B1 versus B2 within A1, we get this black square. And if we average across B1 and B2 within A2, we get that black square. And those are the same on the dependent variable. So there is no main effect of A. Now, is that an okay conclusion? Is it correct to say that the A treatment, whatever it is, let's say placebo versus drug, has no effect on the dependent variable? No, that would not be an appropriate conclusion, right? On the marginal means, it appears as if there's no change. It appears when you average across, let's say, males and females, if B1 is males and B2 is females, if you average across sex, it looks like this drug has no effect on whatever this dependent variable is. Whereas when you look at all the data, of course it does. In males, it increases the dependent variable, and in females, it decreases the dependent variable. So it certainly does have an effect. It just doesn't have a main effect. Is there a main effect of B? Probably yes, because when you average within A1 and A2, that data point is probably different than that one. Is there an interaction effect? Yes, clearly, right? The difference between males and females in placebo is small, and the difference between males and females in drug is big. Or you could say it the other way around. The effect of going from placebo to drug, A1 to A2, decreases the dependent variable for females and increases it for males. So you have the opposite effect of A, depending on what level of B you're in. I'll say that again. The effect of A on the dependent variable, going from A1 to A2, is opposite depending on what level of B you're in. If you're in B1, the effect of A is to increase the dependent variable. If you're in B2, the effect is to decrease the dependent variable. So that is a textbook definition of an interaction effect. It's a difference of differences. Here, lines are not parallel, so probably an interaction effect. But what about main effects? Probably no main effect of A, because if we average across levels of B, we get the same value in A1 and A2. What about a main effect of B? Probably also no. If we average across levels of A, we get the same value for B1 and B2. So if we only looked at main effects for these data, we would conclude nothing's happening. But clearly there's something happening. And that would come out in the interaction effect. Clearly the difference of differences is there. In A1, B1 minus B2 is negative, but B1 minus B2 is positive in A2. So we have an opposite effect of B depending on the level of A. Or you could say it the other way around. The effect of A going from A1 to A2 is different depending on the level of B. If you're in B1, the orange line, going from A1 to A2 increases the dependent variable, whereas if you're in B2, going from A1 to A2 decreases the dependent variable. So again, a textbook definition of an interaction effect. So in a two-way factorial design where you have two factors, independent variable 1 and independent variable 2, and you're testing the main effect of independent variable 1, the main effect of independent variable 2, and the interaction effect of independent variable 1 by independent variable 2, then there's actually 8 different possible outcomes for your two-way factorial design. You could get any combination of a significant main effect in A, a significant main effect in B or not, and a significant interaction effect in A by B or not. So 8 possible scenarios for a two-factor ANOVA when you're testing 3 effects. Another way to think about this is each of those 3 effects, the main effect of A, the main effect of B, and the interaction effect of A by B, each of those 3 effects are independent from each other. They're each testing orthogonal components of your data. The 3 tests, the 2 main effects and the 1 interaction effect, they're testing independent questions about your data. The outcome of one doesn't have a direct impact on the outcome of the other. Here's just some schematics of the different ways you could have those 8 different outcomes. And I won't go through it here. You can look at those. You can pause the video and have a look at those on your own time and figure out exactly how those are working. So let's talk about interpretation of these 3 effects, the 2 main effects and the 1 interaction effect. So looking at the hypothetical data here, if the main effect of A is significant, which it would be here, averaging across B1 and B2 here would be different than over here, and there's a main effect of B that's significant, does it make sense to even ask about the A by B interaction effect, which would also be significant because this difference is different than that difference here? So is the main effect of A meaningful if the effect of A itself depends on the level of B? Does it make sense to average across levels of B if the interaction term is telling us that the effect of A is different across levels of B? And the advice in the vast majority of cases is no, it doesn't make sense. If the interaction effect is significant, then the main effects are not meaningful, even if they're significant. Why? Because the main effect ignores the levels of the other factors. But if there is an interaction effect, it means that by definition, the effect of one factor is different for different levels of the other factor. So averaging across levels of that other factor would not make sense. Again, because the interaction effect is telling you, by definition, your effect is different depending on the level of that other factor. So if you average across it, it doesn't make sense. What about if the main effects are not significant, but there is an interaction effect? We saw this before. Is it true that A has no effect on the dependent variable? Is it true that B has no effect on the independent variable? Of course not. The interaction effect is significant, so the main effects are not meaningful. A does have an effect on the dependent variable, but it's different for different levels of B. And so how do you kind of detect the scenario? Well, you can use your eyes as a first approximation to look at the data, like we are here. But we'll see next week that you use follow-up tests or post hoc tests to test the effects of one factor, like A, at different levels of B. So you can jump in and do pairwise tests in a strategic way to figure out what's happening with the data. But we're going to cover that topic next week. Okay, that's all I wanted to talk about today. So we've seen how including multiple factors in an Anova design helps you by accounting for more variability. And by including an interaction term, it helps you even more, and it enables you to test this third orthogonal question, which is, does the effect of one factor differ depending on the level of the other? And that can be a very important question in different experimental designs, in particular sex and gender differences. Anytime you're testing the effect of a drug or an intervention or some experimental manipulation in some basic science study, we should all be including sex or gender, where appropriate, as a second a fully factorial effect so that we can test precisely this kind of thing, whether there's an interaction between sex or gender and whatever thing that we're studying. If you ask most neuroscientists if the thing that they're studying is different for males or females or is different across gender, in the vast majority of cases, people will say, oh, good question. No, I don't think so. And then if you probe them about, well, what's the evidence of that? They'll say, oh, well, I just don't know anybody who's tested it. So I just always assumed it doesn't matter. But the more and more we dig into this, the more we discover that there are sex and gender differences across many different domains in neuroscience and psychology, which is my area of study. Even across different levels of the organism, all the way from neural circuits and neurotransmitters, all the way up to behavior. So, sorry, that's just the end of my little sermon about sex and gender differences. But it's a good example of where testing interaction effects can make a big difference. Okay, thanks everyone.